Hi, this is Vince from Bryn Mawr College, and today we're going to be working on a conservation of energy problem. So we've got an Atwood machine with two different masses that are released from rest from the same height, and we want to know the speed of each mass when they're a meter apart. So first of all, M1 is smaller than M2, so M1 will move up while M2 moves down. We could also say that since they're connected by a rope, any change in height for M1 is equal and opposite to the change in height for M2. So we have delta H1 is equal to negative delta H2. We could just define that as some delta H. And in this case, it's half a meter because when M1 and M2 each move half a meter in opposite directions, they'll be separated by a full meter. Also, since they are connected by a rope, we could say that their speeds must be equal at all times. So we could set the final speed of mass 1 equal to the final speed of mass 2. We just define that as some v sub f. So previously in physics class, we might have approached this problem by using Newton's laws to solve for the acceleration of the masses and gotten the velocity from there. But in this case, we're going to use conservation of energy. It's a little bit more of a straightforward approach. So we could write down that the initial kinetic energy, T sub I, plus the initial gravitational potential energy, U sub I, is equal to the final kinetic plus the final gravitational potential energy. And since both masses start from rest, we could say that T sub I is 0. So now we can subtract U sub I from both sides, and we get 0 equals the final kinetic energy plus the total change in the gravitational potential energy. And we can plug in the formulas for the kinetic and gravitational potential energies, and we get this expression. Just note that I've plugged in v sub f's for both M1 and M2, and also note that the actual initial and final heights don't matter. All that show up in this equation are changes in heights. So this is why the h equals 0 point is arbitrary when defining the gravitational potential energy. All we really care about are changes in heights when we're concerned with the gravitational potential energy. All right, so now we could use this relationship between delta H1 and delta H2. Plug that in and rearrange, group some like terms here a little bit. And so you can see we have just one term for the kinetic energy of both masses and one term for the gravitational potential energy of both masses. All right, so now we're at a point where we've got an equation with the thing we want to solve for, v sub f, but there's a lot of other stuff going on in this equation. We have to isolate v sub f. So there are many ways to do this. I am going to choose to multiply by 2 over the sum of m1 plus m2. And when you do that, the left-hand side stays 0, but on the right-hand side, what we do is we get rid of the coefficient in front of v sub f squared. So that's useful to us, and the reason I chose 2 over m1 plus m2 is the fact that it is the inverse of the coefficient in front of v sub f squared. So we're one step closer to solving for v sub f. Next, we could subtract the second term on the right-hand side from both sides of the equation, and we get this equation here. And finally, we could take the square root of both sides, and we've solved for v sub f. So finally, just to wrap up the problem, we could plug numbers in, and when you do that, just be sure to use half a meter for delta H. Remember that that is the distance traveled by a single mass, not both of them. And when you do that, you should get that the v sub f is 1.8 meters per second. Okay, so let's take a step back and look at the process we used to solve this problem. The physics we used is really just the conservation of energy, and that brought us to this equation here at the top of the screen. From there, we took a few different mathematical steps to solve for the variable of interest. But all those mathematical steps really just amount to applying the same operation to both sides of an equation. So remember that when you have an equation, when you set two things equal to each other, you could, as long as you apply the same operation to both sides, your new results will still be equal to each other. So that's sort of the basic principle we're using to manipulate this equation and solve for VF. Alright, so if you wanted some more practice with the math skills used to solve this type of problem, why don't you go ahead and do that, and then give the do-it-yourself problem a try.